So today we have our third lecture on wettability, right? Wettability related. And tomorrow onwards, we'll be having, okay, how we can use wettability for applications like photonics, optics related applications, okay? So today, a continuation of our first lecture, I would say. Yesterday we had details like how the particles interact with the liquid surface and all, right? Everything is coming under the umbrella of wettability switching techniques, right? So today we will touch another very interesting approach. It will be a short lecture compared to the previous two, because by 12 o'clock you have the free time to start your report preparation, okay? So have you heard about slippery surface? Yes or no? Some of you might have heard yes, others? No? Fine, no issue. That word is not so complicated, right? Slippery surface. Then what could be it? Right? The definition is straightforward, right? You slipped there, right? You hope you are okay. So, that's true. You are the droplet there, right? That's it. Because we are, in our case, we are not thinking about human beings. We are, droplet is our, what the point? Okay, so what he told is correct. Okay, so let us put it in a smaller dimensions. Okay. Okay, so as a connection slide, I put some, so that I can ask some questions to you. It's always nice to have that, right? Okay, so our third lecture on wettability. So I hope we are all in a matured state to appreciate nature better, right? Unfortunately, rain stopped when we understood about interactions better. Hopefully, it will come back today. Okay. So then let us start, okay, just to go through it, just to have a connection slide. So our initial idea was, okay, liquid-solid interaction, we have to understand, we started with the surface, right? Then we understood, okay, how chemically, physically modifying the surface, hydrophilic, hydrophobic, right? Then in terms of application, it's huge, right? Starting from painting, you just imagine, you have actually a paint which is not, you studied about the spreading factor should be greater than 0, less than 0, all these conditions, right? So you just imagine you have a paint which is not spreading or it is having a de-wetting property. You will not get a film, right? There will be islands, right? Okay, it's a good design. But that is not our purpose, right? If you are painting your car, you don't want any. It causes drag also, right? That's what I want to connect. Because you think about high level aerodynamics and all. The coating is super important, right? The painting. So then printing, everywhere. I don't need to explain it explicitly. Textiles, windshield, right? Or then marine applications, anti-fouling surface, because the fungi and all other things would like to stick to the body underneath. So we want to prevent, otherwise it will lead to corrosion and huge catastrophe, right? And huge amount is being spent to clean after every trip. Okay, so read some news on this kind of things to appreciate why we need to study about matter and wettability. And aerospace, I already told you, anti-icing surface. One of my friend is working in Airbus. He says, okay, problem is like, you can make a coating in the lab. Okay, it works as anti-icing. Okay. The problem is like when you take it in the field, it has to withstand extreme conditions, right? In terms of the wind speed, in terms of the temperature, in terms of the rainy, right? And most of the times it breaks. Then that is even worse, right? Because if it breaks, it makes, nucleation sites where it accumulates, right? So that can lead to more catastrophe. So the coating stability at extreme condition is like, if you can find a way to do that for aerodynamics, people, you will be a millionaire. Okay. So self-cleaning materials, I hope everyone understood what is self-cleaning materials. Okay. Then tissue engineering, biological application, because the surface wettability, if you think in terms of the chemical way of surface wettability, it all depends on the hydrogen bonds and all, right? So then preferential accumulation of biological cells, you can make a gradient of biological adsorption. So all these things are possible. And microfluidics in general, we mentioned about many different aspects. Damien also mentioned about the different aspects of microfluidics where wettability is like, without understanding wettability, most of his applications won't work, right? You might have seen a droplet running in between a black, right? As a very simple experiment he published in Langmuir with a marker pen. Got the point. So idea is important than facilities, right? We always complain we don't have facility to do the research, but first idea is important. Okay, so let us start with that basic. So let's recall from previous lectures on wettability and loading. Yes. We were mainly saying or appreciating, the hydrophobicity, right? Everything require hydrophobicity. This was our, in the field also, when we land into the field, this is our field, okay? If you can prepare, fabricate a super hydrophobic surface, okay, my world is done, okay? Because water falls on it, it goes a self-cleaning surface. Low hysteresis, I'm done with my job. Is it true? Is it always required to be like that? Look at the nature. Whether nature likes super hydrophobic people always? No. So that means, fabricating or replicating lotus leaf alone, right? And unfortunately, lotus leaf structure is also not mechanically so stable, right? Because you have to have grooves, right? You have to have patterns, right? That means that is fragile to, suppose, some force applied on it. You know the pencil transaction, right? Pushed inside is fine, fine. So we can categorize the issues. Limited functionality. Okay, what does it mean? It's a very simple word, right? Explain that. Because we have already had more than 3 hours, 3.5 hours, we had a discussion on wettability, right? So tell me, because now today, yesterday and day before yesterday, we were appreciating hydrophobic, super hydrophobic, low hysteresis, right? Today we are going to put him under the other side of the, okay? So let us discuss about, okay, what are the disadvantages, challenges with the hydrophobic sulfur? Limited functionality. What does it mean? Yeah, so that means certain program. If you think about the Damien's word, you design a surface for a specific liquid for a specific contact angle of hysteresis. That's all he will do, right? Got the point. So, but in real life applications, you need to have some sort of bit more flexibility, right? Especially Banu created a surface 78 years back before penny pump coating. It was like a 160 degree with the contact angle less than 1 degree, right? Or close to 1 degree. You remember how much we had to struggle to measure the hysteresis or to keep the droplet on the surface? Suppose you want to do a reaction on a surface, you need to keep the droplet on the surface, right? And you think about a droplet having a super hydrophobicity. That means contact angle will be very, very, very less, right? But if you think about a reaction, you need a contact area, right? Got the point. So that means, the super hydrophobicity or the lack of hysteresis is not the real ultimate thing, right? And another thing we discussed about droplet transport, right? When we discussed about the droplet transport, what are the two forces we discussed? In lecture number 1, we mentioned about the different forces experienced by the droplet, right? Under different conditions, if you have a gradient in wettability, if not, what are the forces, right? So suppose you want to transport a drop, right? That's one of the application, right? That means what are the forces acting on the droplet? You have that wettability gradient, right? Gravity is acting on it. If it is a tilted surface, then the send the hysteresis force, right? So for the droplet to get transported, basically what is actually the basic criteria we defined on that day? Is it anything connected to superhydrophobicity? In that expression, do we explicitly say superhydrophobicity? No, right? The only criteria we told is, okay, there should be a gradient in contact angle, right? That will lead to the wettability gradient force. It can be due to tilting, it can be due to inherent wettability gradient on the surface, chemical or physical inhomogeneity. Then the most critical criteria was the hysteresis, right? The force due to the hysteresis. So these are the, physics-wise, this is the only two criteria you have to satisfy. Your wettability gradient force should overcome the hysteresis. But you see, if you look at the literature, you see a lot of effort is being devoted to fabricating superhydrophobic surfaces, right? Yesterday, one was saying about the mushroom, right, to make a slippery, but that's also superhydrophobic on the other side, right? So the question is it the right approach? The answer is no. Okay? And nature also says we don't need superhydrophobic always. Okay? So with that, connecting to nature, let us go to the next point. Not self-healing. What does it mean? Because in nature, we are all prone to damages, right? Injuries, right? We have to heal, we have to self-clean, right? But if you make a structure with a PDMS, even if you press too much, it will not come back to the exact position, right? You say, okay, it's elastic, it will. There is always hysteresis in nature, right? Got the point. And I told you, if you press, Cassie to Wenzel transition, right? That means entirely different functionality, right? Good. So self-healing is actually one of the issue we are facing with the superhydrophobic structures. Then limited to certain type of fluids. You see, we were smart enough last 2 days so that we were only discussing about water droplets, right? But in this world, many other droplets are existing, right? Oil you take. You take a superhydrophobic surface, let us take the Arjun, do we have a spare sample by Banu? And you put a oil droplet there, water will be superhydrophobic, right? Oil will be completely wetting, right? Oil will be completely wetting, and how it wets, basically we have that, the wetting criteria and all we discussed, right? It all depends on the interfacial energy, surface tension of the droplet. And there was a discussion, one student came to me about the role of interfacial tension. We usually say, if you have a surface, inherent surface 90° or above, if you make structures, it can lead to Cassie-Baxter state. And if it is below, typically it leads to Wenzel state. It will, because it can penetrate to the pores. It's very simple logic. I hope up to that point it's clear, right? So limited to certain type of leak is problem. So then the question is can we make a universal coating? That's also a problem, right? Let us see. Hysteresis, good or bad? Tell me whether hysteresis is good or bad. Depend on such situation, right? Because if you are a lotus, you would say hysteresis is bad for me, and if you are rose, you would say yes, I need a hysteresis. Or beetle, because if the droplet accumulate and if it randomly goes, it need a frictional force so that it gets enough time to grow the droplet and direct it. That means hysteresis in one direction should be high compared to the hysteresis in another direction. So, rightly pointed out, you have to see where we use that word, right? So then, last one is is the superhydrophobicity is necessary for droplet transport or controlled droplet transport? I would say no. Because if it is superhydrophobic, controlled is gone, right? Because in a minor tilt or the impact, it can simply jump back, right? So it's better let the drop interact to the surface for some time or to certain contact area, then decide whether to move. Okay, we have to compromise the speed there, right? So it's better you have some sort of a give and take policy between these two. That's where nature introduced another type of surfaces called slippery surface. Yeah, so let us go through this. Yes, lotus leaf. This is for certain. I think all points I mentioned in the previously. This is for slide purpose. Okay, and the structure fabrication remains costly and impractical. For large, you take about a fabrication of large surface. Okay, and even 3D printing is problematic there, right? Slippery surface, I am not claiming it's large area, but still there are ways to do it. Okay, one approach I will show you later. Okay. Okay, so then let us critically analyze Wenzel and Casey models. Even with that, the projected surface area, we discussed that in the first lecture, right? So this is how it works, right? So you have actually, I would say, lotus leaf on the right side, and it is having, this is another point you have to take care. The material with which we fabricate the structure is also important. So in the case of lotus leaf, there is a wax coating on it, not only due to the structural, and the one we see is actually a microstructures. But in addition to that, there are even smaller structures present. So what we see is a collective effort of all these features. Okay, and in the case of Wenzel, the material should be having a property so that the liquid will be able to go inside, and that can be done either by droplet volume, controlling the pitch, right? Because you think about the right hand side figure is physically wrong, right? Why? I would say I have drawn it, but that is physically wrong. Something is missing there. Anyone can identify? It is this. I have drawn is flat, right? How it should be? Okay. So you are drawing. You are saying drawing something like this. You are saying about this is what the droplet makes, right? Let's find it. So this is my substrate, right, on the bottom, right? And this is my, I would say, PDMS, okay? And this is air, right? And you are saying the liquid should take a form like this, right? It should definitely have a curvature. In which direction is confusing for you, right? Anyone want to help her? Not Banu for sure. Because if you go to micro scale, the one I have drawn is not correct. I accept that. And to have this one, you need a pressure from bottom, right? Otherwise, how that is possible, right? To acquire such a shape, gravity acts on it, right? So it will try to have a curvature like this. Got the point. Typically, this is a, okay? Because it is hydrophobic, but a weight is acting on it, right? And this is air, right? So it's always, try to push it down. So the meniscus, there is existing not a flat meniscus. And this shape actually is beautiful, right? This, how much is the curvature is the balance of the forces acting on it, right? Gravity, surface tension, right? That means, if you know the shape, you get everything, right? Because included the contact angle is included. It's a three-phase contact line, right? Exactly like your contact angle, right? And this is where the problem starts. Yes. Because the Casey to Baxter Wenzel transition, you can realize in multiple ways, right? Okay, you reduce the surface tension of the liquid. What is going to happen? Then the surface and the liquid is actually having more liking, right? It will try to float or it will try to wet, right? So that can lead to transition. If a transition happens, the property is entirely different, right? That means a droplet, water droplet with a tiny amount of surfactant or some sort of dust can have this transformation to the other one, right? Then you think about the other one. Suppose some humidity got trapped. Got the point? Suppose some humidity got trapped. This can, because it's like a confined medium, right? Closed structure, right? It can get condensed this region, right? That can actually lead to the transition, right? Then you are saying somebody designed the surface for you, you are not so careful, and you put some extra volume. You can actually press it, right? You can go like this. You shake it, suppose you are transporting. Then your structure also can wobble a bit, liquid also wobble a little bit, right? So these all can lead to this transition to Wenzel. If it happens, the whole purpose is gone, right? And there are wettability switching surface from one state, the other state can be gone. But typically I am saying, even though paper says, don't quote it. Paper says reversibility, but reversibility is nearly impossible. Because once the liquid goes there, because from this state to this state, you need some structural transformation, right? Some structural change, right? Once it goes there, even though structure comes back, it is happening inside the liquid, right? It will not come back. So the repeatability, including me, we are claiming, is the one a new experiment. Okay, remove that droplet, keep it at a vacuum or high temperature for certain minutes. Do that experiment again it's super hydrophobic. Reversibility is like a bit of a tricky, because it's a part of the nature, it's part of the physics, right? So we cannot, but there are ways to do it. Okay, I hope it's clear. So then the point is, these two situations are not solving the problem completely, right? Because we want a kind of, sometimes we want to keep the droplet at a certain point, we want to guide it. So then nature is having another approach in terms of structure, wettability, hysteresis, everything we discussed, right? Applicability, everything, okay? So now nature is having another approach. Have you heard about this guy? Nepentheus? He is having an entirely different approach. Anyone knows about how it works? Arjun is pitcher plant, right? The other plant name? Pitcher. Yeah. And he can eat insects. How it happens? How the insects get trapped? Yes? Small grooves.
So basically, the leaf of the plant is the active component. It's insectivorous, so it's pitcher shaped. The rim of the pitcher has some enzymes that are sticky. So when an insect,
it's sticky.
Yeah,
it's sticky. That's the point. Okay.
Yeah.
Because grooves alone will not solve the problem. If you think about an insect,
yeah,
he can simply fly away, or if it's an ant, he can climb up.
So the grooves are present in the lower part of the leaf. So once it falls into, it can't come back. So that.
So ultimately, I would like to take your word sticky. Okay. So what happens is, there is actually an oil film present, sticky. I would say just use the word oil film to have a feel. Okay. Then the question is, how that oil film or the lubricant film, that is the better terminology we use, okay, can be stable. Like, you keep an oil, you keep a lubricating surface. So you take a glass plate, put an oil. That's actually lubrication process, right? But if you tilt, slowly that will come down, right? So how we can keep that layer intact is the question, right? Nature does that also. So what happens is, this is what happens. You see, you have actually a structured surface, right? As she told, like, that you have actually structures inside as well as the outside. Okay. Then that is actually coated with, there is actually a waxy liquid lubricant layer present. Fine. Can you tell me what should be the criteria for selection of this lubricant layer for nature or for this plant? Because any liquid will not do the job, right? There should be some specific criteria need to be satisfied to have this is called slippery, okay, induced surfaces, because it goes to the pores, okay, porous surfaces or rough surfaces where the liquid goes. Is there any criteria we need to understand or appreciate while we think about designing such a surface? Because you studied the fundamentals. That's why this question. Because what is my aim now? I have a porous structured surface, I would say. I want to have a layer of oil stably, right? It should be stable. It should not make a droplet. It should not deviate, right? There should be a layer present. So then if you are doing a research in that direction, okay, well, in which way you will start? Because you have to find a surface and you have to find a structure, you have to find a liquid which matches something, that's for sure, right? Randomly we cannot do a number of combinations and select, right? There should be some design criteria, right? What should be the first one? Okay, you have to fix some material, then accordingly you have to work on the other material for sure. It should be totally wetting. So must stably adhere to the surface. Okay, it should be completely wetting. Yeah. So you remember this slide, right? In the first lecture we had this slide, right? So which tells you about the spreading, right? So it should be completely spreading and wetting to the surface. That's the criteria number one. That means you have to decide the surface, you have to work on the surface energy of the liquid, solid, also on the porosity, right? It's a beautiful thing you have to do. To get into the pores, you have to apply vacuum. Otherwise, there will be air bubbles. It's a practical thing you have to do. Keep it in desiccator, vacuum for 1 hour. Normally, the air bubbles trapped in the structures will be taken out, so that the impregnation really happens. Once it goes there, since it's wetting, it will stay there, and then you can keep it in a tilted angle for a long time, so that the excess layers will be removed. Still there will be a monolayer, and the liquid inside the pores will remain there. Okay? So then you can see an yellow region which was not there in the previous case, right? The Cassie and Wenzel states, right? This is because he can actually, they are immiscible, you see, stronger ability to wet to textured solid surface than the liquid to be repelled. We mentioned that, right? Then lubricant and liquid surfaces must be immiscible. Some condition needs to be satisfied always. How it forms? Because this is a liquid-liquid interface, right? Got the point. So definitely at the three-phase contact lane, they will interact, right? So they will acquire a shape which they feel energetically stable, favorable. Okay, that's what they do. So depending on the viscosity of the liquids, interfacial energy of the liquid, some cases we can see very high ridges, some cases very small. Okay. So this is the typical design of this plant. Then when an ant goes there, I think I have an image, not myself, took it from a No? Yeah, took it from a review article. So you can see two different types of nanostructures, right? It is nice to have a structure so that the impregnated liquid will be stably adhered, right? Because it's not easy to come out because of the Laplace pressure and all, right? So then you see an ant. An ant is able to climb, right? And finally he falls down, right? You can see a jam or droplet also they placed. This is the working principle. This is how actually an ant or insect placed on this plant, because it's having this nice shape, right? And once this poor guy's legs are there, and it's so flexible, poor guy, right? And this liquid can really cover it and even deform it, right? He is not having sufficient force to take off anymore. Then there is a curvature. He is having a bit of weight for sure. Slowly, the only thing he can do is glide down his sliding process. It can be droplets, it can be insects. Then after that, basically, as she told, there can be enzymes, which I don't know anything about that, how they digest, how they kill the molecule. But what I know is basically how they guide their food to the point. So this is what is happening. It can be completely, you don't need a ordered structure. It can be a completely random structure also. You take a glass plate and you rub it. But the thing is, some 50 micrometer depth is required. Using sandpaper, you can rub it really deep. And you use a low viscosity oil, apply a film over it, spring coating or applying, then keep it in vacuum for some time, like 1 hour, then the all air bubbles are escaped. Then you keep it tilted for a long time, like 1 day typically. Then the excess oil will be removed and the remaining surface is your replication of this, straightforward for fabrication. Okay, so then this is for giving you slides, like, in that reference, you can see different combinations. And you can see a striking difference now. In the previous classes, we were discussing about the hydrophobicity, sliding angle, contact angle, and all, right? You see here, the contact angle typically around 100, 120 only, right? It is not about 160, 170. What the point? And the sliding angle, it tells you at what angle the droplet starts to slide. You can see it's very small numbers, right? In some cases 8, otherwise it is 2, 3, 4, this kind of things, right? It tells you that even though there is an oil layer present, slight tilting, but in the case of a normal solid surface, it will not happen, right? Let us do an experiment here. Arjun. Let us start with a pristine PDMS. Other side we can take. Okay? So this is a PDMS surface, okay? Banu, when you will be giving demo? We will be giving a soft lithography demonstration also, okay? So what is the expected contact angle for PDMS? PDMS is a well-known, famous material, soft matter, with microfluidics, people knows, right? Inert, transparent, hydrophobic. Okay, good. Anyone have any guess? Yeah, in 10 minutes I have to wind up the lecture. So anyone have any guess? Tell me. You are in a unstable state, I told you in the first day itself. Is it 10 degrees? Huh? That you can immediately say no, right? This is more than 90 for sure, right? Huh? Because the angle is like this, right? That is the first thing our brain process, right? So it's typically 110, 90, 95 to 110, depending on the liquid, depending on the ratio, because it's like a cured one, right? So it's hydrophobic, okay? So now you do, it is having a relatively high wetting, right? Hysteresis also, right? So the sliding is difficult. Now let us go to the, and he made some structured surface on the other side. You can see the contact angle is slightly better, okay? You can see the center, and let me do this process. You see, even though it's structured surface on an area which is no structure also having a very high pinning force, right? So yours is actually Wenzel. Contact angle is improved compared to the pristine. You can see even at 90 degree I keep both the droplets are there, right? Yeah, and even the other guy escaped. The one on the uncoated region escaped, but his coating is really sticking, right? So it's a very good Wenzel state. Maybe it's a negative, positive, we don't know. Okay, I hope it is clear, right? How it works. So let us see how the slippery surface works. I hope it is clear, a pristine surface and a structured surface. Now we are going to make a slippery surface with the same material on that structure. It will work. We did it in a very crude way. No. Let us see. In which direction? I will see. Okay. You come where I should put the drop because my eyes are old, right? Center? Somewhere there. Okay. So I have to put it on the pattern, right? Okay. I hope it will work. Okay. So you can see a droplet, right? Over it. As you see sliding. And it's having high, low contact angle, but it slides well at a very low tilted angle, right? You remember the previous case? The pristine PDMS had to do almost 90 degree to take out the drop, and his structured surface was not able to do even at tilted surface. Now, even at like a 10 degrees, 20 degrees, right? It's not the optimized situation, but it works, right? It slides, right? You agree with me, or I am doing any manipulation? Who want to do this experiment? It's real oil dewetting. Because we haven't put it in vacuum, right? So the dewetting should happen. So you should know the physics. Okay, so let us do one more time. Anyone want to do? Because we haven't kept it in vacuum, right? So the dewetting chance is there, right? So I'm just demonstrating physics. Huh? Okay. So I am keeping my droplet. Let it be slightly bigger. Why I keep slightly bigger? Why I keep slightly bigger? Because my driving force is gravity, right? So you see, it starts sliding, right? Very nicely. The angle is very small, right? Even before I reached this one, he was able to move, right? You see the difference between three different kind of surfaces now? Now you imagine the lotus as well. So 4 different types of surfaces you have seen, right? Suppose a situation arrives where you want to have a complete control over the direction and the reaction time to the surface, and you want a sufficient contact area, And you are not bothered about velocity. How fast it happens, I'm not bothered. Because certain reactions require time, right? So just by controlling the tilt angle, the droplet can be placed, because it's an on-off situation, right? And you have a flexibility of 5 degree. So 5 degree, if you go to 4 degree, droplet stops. You go to 6 degree, droplet starts to move. So you have much more control than your lotus leaf, right? Because lotus leaf only tolerance is 1 degree, 2 degrees. You cannot control. Even our measurement is having more than that. Error is more than that, right? So in 5 minutes, I hope it is clear, right? So now let us quickly go through how we can fabricate, okay? So this is what I have shown, okay? So if it is a normal surface having hysteresis, there will be stains, right? When the droplet after hysteresis is over, it goes, there will be small amount of liquids present, and it's not good, right? You think about you are collecting food. You are losing food then, right? Which I don't want. So you think about a slippery, nothing will be kept there, right? Because each and every position, the liquid acquire its own shape, and there is a driving force. You can write the free body diagram or Lagrangian approach to find out the velocity of transport. It's possible, okay? Okay, I hope it is clear. Fabrication is also clear. Then, how to make them stimuli responsive? Last 5 minutes. How to, because actuation, programmability, reconfigurability is Damian's motto, right? So how you can make it reconfigurability? You have heard a lot of lectures now, right? What are the possible actuation methods? You can apply electric field, you can apply magnetic field, you can apply light, you can apply temperature. Okay, there are a lot of ways. Suppose your structure is having some magnetic nanoparticles. Then if you apply a field, this structure will tilt toward one direction, it can induce a flow, right? Suppose electric field, it is responsive to electric field, it responds to temperature. Depending on the material, thermal expansion, the contraction, everything can be used, right? Because a local variation, here the trick is, you will go to that tilt angle just above the critical tilt angle. So if the critical tilt angle is 4 degree, you will go to 3. Stay there, droplet is staying there. Then you need to apply only a tiny perturbation to start the motion. This is the trick. We will not keep it here to do this, okay? So how to make stimuli responsive, you already have a lot of ideas. So that's why there is no slide for that. Next question, or the last question for the day. Arjun, 1 second. Is porosity is mandatory? The question is clear, right? Till now we were mentioning, okay, you need to keep the lubricant layer stable, right? That's why I was doing that experiment very fast, right? I was, trying to convince you at the earliest, right? Because there is a chance of de-wetting, right? Because I haven't put it in the vacuum, it is not completely gone to the pores, right? So that the layer will try to de-wet and make droplets. Because, they are not energetically stable if it is a flat film, unless it is impregnated, right? That was the hurry I did. Is it required? Is it always required? 5 seconds. Only 2 answers possible, right? Yes or no? How many of you believe yes? There is no half answer in this world. Yes or no? Okay, yes believes only 4 people, and they are safe now because porosity already is seen, right? So others, please explain me without porosity how you can make wettability impregnated surface. Tell me. More than 90% believe porosity is not mandatory. That's good. Because I don't need to spend money to make porosity, right? But tell me how. I hope I haven't seen the invert. Many of you told the porosity is not mandatory, right? Tell me how. Because if porosity is not mandatory, I can demonstrate that problem as well. Okay? So this surface is having no porosity. Okay? This side. Yeah, side is having no porosity. Okay? I'm putting a drop. This is an oil drop. Okay? And I can make slippery surface very fast. You see, I just do this. This is a slippery surface. Okay? But after a few minutes, you will see the deviating. Okay? You will see small droplets. Yeah, you already started to see, right? You can see, it starts to form droplets, right? You see? You see, it's already started forming droplets, right? You can see large clusters now, right? And you can see the deepening process. One droplet here, a large droplet here. You see? And if it was porous, it will not happen, right? It will go to the pores, right? Then it cannot deviate because in the pores, the hysteresis is very high, right? Then what could be the solution? It's already droplet form, right? It's not a film anymore. Tell me, I have to leave. Whoever committed should answer. How? It is possible. We have a paper on that. Okay? That's what the coming 2 slides. Okay? Last 2 slides. Yes, that's the point. You have to create, you have to functionalize the surface. That's what I told you, large area coating is easier in this approach. Because chemical functionalization is relatively okay. We can deep and you can etch. Right? It's fine. This is what we did, and it was one of the first approaches in that direction. 2014, we did it in Germany during my postdoc time with one of the best PhD student in our group. And it's very highly cited. Very simple approach. You will laugh after seeing this one. Okay? Next slide is actually the approach. You see what we did? We have actually a substrate. We cleaned that with acetone. Okay, fine. Then put a silicon oil having some viscosity, which you have to work on it. Why I use 5 centistokes viscosity. Read that paper. There's a motivation so that I may get some more citations. Okay. So then, okay, I told you, like, what you have seen, it will not be a stable film, right? Because it will try to deviate, it may make droplets. So spread it and heat it for very short time, something like, 3 minutes, so that the droplet is having, this layer is having no chance to deviate. Because especially when you heat, a lot of other phenomena also happens which helps spreading. Then after this one, what happens is, there is a very monolayer of silicon exists. You have a glass, which is having a bit of affinity towards this one, this compound. And then you have a silicon layer. Okay? And this silicon and the silicon oil and the silicon layer are chemically same, right? And if you put a silicon oil over this one and keep it, there will be a monolayer always present, right? Because he is not seeing any sort of enemy. Because deviating will happen when you have energy mismatch, right? So I am as exactly like what he told, chemically functionalizing the surface so that your impregnating layer will not see the difference in energy. He will spread, right? And once he spread, okay, if it is a large paddle of drop, it will deviate, it will flow, but there will be a layer present. It will be stable, right? Because they are chemically strong, right? That's what, very simple one. And you see, this is how it looks like. The first one, if you have a very thick layer of impregnating layer, you can see the one I have drawn in the past, that yellow one, right? And it exists. And if you have a very thin one, still you can see on the edge, right? A very baby is present, right? Because it's a part of the physics, right? And this is having huge importance on the hysteresis because it really prevents also, right? Then you can see the velocity as a function of tilt angle. You see the droplet, depending on the different viscosity, at a 2-3 degree tilt angle, it starts to move, right? That means now you have a surface having a contact angle of 90 degree and a hysteresis of 3 degree. This is amazing, right? Because contact angle of 90 degree means, this is one of the most desired structure where you have a large surface area you can do. And this 3-4 degree contact angle means you have sufficient control over it and you can control the velocity as well. It's amazing, right? And the velocity as a droplet volume, it should increase because that gravity is the driving force, right? There is no surprising thing, but in paper we put it. This is interesting. Okay? What we did is very interesting experiment. So you have a slippery, yeah, people will be waiting, I will just finish. Okay? You have this slippery surface and you put two droplets having different volume. One is 10 microliter, the other one is 20 microliter. Okay? So then I apply a temperature gradient. Okay? Temperature gradient. There is a chance that, this oil film itself can move, right? Because there's a liquid form, the Marangoni flow can exist, which we will discuss later. So if it is happening, both the droplets should move in the same velocity, right? But here the elder brother is moving much faster than the younger one, right? Which we believe the opposite should happen, right? Because he can sense the more gradient, right? And it moves. It's interesting. And even this transport is possible even in a tilted geometry. Because if you do this like this, it will go away. But if you do exactly the opposite, it will hang. Which is not possible with our conventional superhydrophobic surface, right? So the slippery surfaces have a lot of advantage, but it's not solving the entire problem of wettability. Okay? But we try to mimic nature again and without any porosity, because impregnated in slippery surface, we always believe porosity is mandatory. It is not mandatory, and it works amazingly well even without any porous structures. Okay? I think we already summarized the topics in the last three talks related to wettability. I think we covered nature in a decent manner. Thank you.